far beyond the familiar pinpoints of light that make up our night sky. In a quiet and unassuming stretch of the constellation Leo, a faint alteration in infrared light finally reached Earth. That signal had been traveling through the darkness of space for more than 100 years. At first glance, it seemed insignificant, just another data set, another stream of numbers buried among the trillions collected by the most powerful telescope humanity has ever built. But hidden inside that light was something no one expected. A chemical fingerprint that does not belong to rocks, storms, or oceans, but to life itself. The James Webb Space Telescope had just identified a world so precisely balanced, so chemically active, that astronomers reached a level of certainty almost unheard of in their field. This wasn't a tentative signal, not a maybe, not a distant possibility. It was a planet that appears fully habitable, and potentially even more welcoming to life than Earth itself. What Webb has uncovered doesn't merely suggest that life could exist somewhere in the universe. It strongly implies that we may have finally found it. The breakthrough arrived quietly, buried deep inside infrared observations recorded as a distant planet passed across the face of its star. As that starlight filtered through the planet's atmosphere, certain wavelengths were absorbed, leaving behind a precise spectral signature. At first, the results looked familiar. Scientists identified water vapor, methane, carbon dioxide, each molecule significant, each one suggestive. Then came the molecule that changed everything: dimethyl sulfide. On Earth, this compound is produced exclusively by living organisms, not by volcanoes, not by lightning, not by non-biological chemistry. Life, and only life, creates it. And the signal Webb detected was not subtle. It was strong, strong enough that the probability of false detection dropped below 3 chances in 1,000. In a field where uncertainty is the default state, that level of confidence is extraordinary. The planet, designated K2-18b, orbits a red dwarf star roughly 120 light-years from Earth, sitting directly within the region where liquid water can exist. But unlike the rocky, Earth-like world scientists once believed were required for life, K2-18b belongs to an entirely different class of planet. It is a super-Earth, larger, heavier, and wrapped in a thick, hydrogen-rich atmosphere. And instead of making it hostile, that atmosphere may be exactly what makes it ideal. K2-18b is not perched on a fragile knife's edge the way Earth is. Its environment appears remarkably stable. Surface temperatures hover around 120 degrees Fahrenheit, warm enough to maintain liquid water, yet cool enough to prevent oceans from evaporating. This balance is not accidental. The hydrogen-rich atmosphere acts like a planetary blanket, trapping infrared heat and redistributing it evenly across the globe. Unlike Earth, where temperatures swing dramatically between day and night, summer and winter, this world may experience consistent conditions planet-wide. Even the night side, locked in permanent darkness due to tidal locking, remains warm enough to support liquid water. Gravity plays a crucial role. With nearly 3 times Earth's surface gravity, K2-18b holds onto its atmosphere with ease, preventing it from escaping into space the way Mars lost its atmosphere billions of years ago. What feels extreme to us may actually be an advantage. Strong gravity, thick atmosphere, stable temperatures. Together, they create an environment where life does not need to constantly struggle for survival, but can instead focus on growth, complexity, and long-term evolution. The star hosting this planet is a red dwarf, smaller and cooler than our Sun, yet vastly more enduring. While our Sun will eventually expand and wipe out all life on Earth, red dwarfs burn steadily for trillions of years. That means any life that emerges on K2-18b is given an almost unlimited window to evolve. The planet completes one orbit every 33 days, sitting close to its star while receiving nearly the same amount of energy per square meter that Earth receives from the Sun. This places it firmly within the habitable zone, but with one critical difference. Around red dwarfs, habitable zones persist far longer than around Sun-like stars. Add to that K2-18b's thick atmosphere, which shields the surface from harmful radiation and distributes heat globally, and it becomes clear why scientists are now rethinking everything they once believed about habitability. This discovery suggests something radical. Earth-like planets may not be the best places to look for life, after all. Instead, the universe may favor worlds that are larger, warmer, and far more stable than our own. What truly elevates this discovery is not just the planet's temperature or location, but the behavior of its atmosphere. The detected gases exist in a state of chemical imbalance. On a lifeless world, these molecules would react with one another and disappear. But on K2-18b, they persist in large quantities. On Earth, this kind of atmospheric disequilibrium is sustained only by biological activity. Life continuously injects gases into the atmosphere, preventing it from settling into chemical equilibrium. K2-18b shows the same pattern. Even more telling is the absence of ammonia, a compound that should be present in lifeless hydrogen-rich atmospheres. Something appears to be actively removing it. Something alive. If this interpretation holds, then we are not observing a planet where life might arise someday. We are observing a planet where life is already reshaping the environment on a global scale. A living world breathing across interstellar space, detectable from 120 light-years away. The planet completes one orbit every 33 days, sitting close to its star while receiving nearly the same amount of energy per square meter that Earth receives from the Sun. This places it firmly within the habitable zone, but with one critical difference. Around red dwarfs, habitable zones persist far longer than around Sun-like stars. Add to that K2-18b's thick atmosphere, which shields the surface from harmful radiation and distributes heat globally, and it becomes clear why scientists are now rethinking everything they once believed about habitability. This discovery suggests something radical. Earth-like planets may not be the best places to look for life, after all. Instead, the universe may favor worlds that are larger, warmer, and far more stable than our own. What truly elevates this discovery is not just the planet's temperature or location, but the behavior of its atmosphere. The detected gases exist in a state of chemical imbalance. On a lifeless world, these molecules would react with one another and disappear. But on K2-18b, they persist in large quantities. On Earth, this kind of atmospheric disequilibrium is sustained only by biological activity. Life continuously injects gases into the atmosphere, preventing it from settling into chemical equilibrium. K2-18b shows the same pattern. Even more telling is the absence of ammonia, a compound that should be present in lifeless hydrogen-rich atmospheres. Something appears to be actively removing it. Something alive. If this interpretation holds, then we are not observing a planet where life might arise someday. We are observing a planet where life is already reshaping the environment on a global scale. A living world breathing across interstellar space, detectable from 120 light-years away. For decades, the search for life beyond Earth followed a rigid blueprint. Scientists believed that to find life, they needed a planet nearly identical to Earth, similar size, similar mass, a thin atmosphere, a rocky surface, and a sun-like star. K2-18b shatters that framework in a single discovery. This is not Earth's twin. It is Earth's oversized, unfamiliar cousin, operating under conditions once assumed to be hostile to life. With a mass more than 8 times greater than Earth's, K2-18b belongs to a class of planets known as super-Earths. Worlds that were once dismissed as bloated, gas-heavy, and incapable of sustaining biology. Yet the data tells a very different story. The planet's immense gravity anchors its atmosphere firmly in place, preventing the slow erosion that doomed Mars. Its thick hydrogen envelope, once considered incompatible with life, instead creates a stable thermal environment that preserves liquid water across the planet. This forces a profound shift in perspective. Habitability may not be about fragility and perfect balance. It may be about resilience, mass, and long-term stability. K218b suggests that the most life-friendly worlds in the galaxy are not delicate copies of Earth, but robust planets built to endure for trillions of years. Beneath K218b's hydrogen-rich sky may lie one of the most extraordinary environments ever discovered. Vast global oceans, potentially hundreds of miles deep, composed of water mixed with dissolved hydrogen under immense pressure. This is not an Earth-like ocean confined to shallow basins. This is a planetary ocean, dwarfing all the oceans of our solar system combined. Hydrogen fundamentally alters how this ocean behaves. Dissolved hydrogen expands the range of temperatures and pressures under which liquid water can exist, allowing stability far beyond Earth's limits. Where extreme pressure collapses biological structures on Earth, hydrogen on K218b may act as a buffer, maintaining conditions suitable for chemistry and potentially biology, even at staggering depths. This opens the door to ecosystems of unimaginable scale. Life would not be restricted to coastlines or surface waters. Entire biospheres could exist layered through the depths, thriving in warm, chemically rich environments where energy is abundant and stable. Evolution in such an ocean would not be constrained by scarcity. It would be accelerated by abundance. The most unsettling implication of Webb's observations is the sheer strength of the biosignatures detected. Dimethyl sulfide does not linger quietly. It breaks down rapidly under stellar radiation. On Earth, its continued presence requires constant replenishment by living organisms, primarily across vast oceanic regions. For Webb to detect dimethyl sulfide from 120 light-years away, biological activity on K218b cannot be localized. It must be planetary. This is not a world where life survives in isolated pockets. It is a world where life dominates atmospheric chemistry. The concentrations detected imply a biosphere operating on a scale far beyond anything humanity has ever experienced. Entire oceans breathing, metabolizing, reshaping the atmosphere continuously. This is not the faint whisper of microbial survival. It is the roar of a thriving planetary ecosystem. K218b does not merely host life. It is shaped by it, and the implications extend far beyond a single planet. Red dwarf stars make up roughly 3/4 of the Milky Way's stellar population. If even a fraction of the planets orbiting these stars resemble K218b, then the number of potentially habitable worlds in our galaxy increases not by tens, but by hundreds. Worlds once written off as too massive, too hydrogen-rich, too alien, are suddenly reclassified as prime candidates for life. The universe may not be sparsely populated with rare, Earth-like oases. It may be densely filled with super-Earth water worlds, each wrapped in thick atmospheres, each stable for trillions of years, each capable of hosting biospheres far more mature than Earth's. The discovery of K218b forces a radical conclusion. Life may not be the exception. It may be the default outcome wherever physics allows stability, water, and time. And the James Webb Space Telescope has just given humanity its first clear glimpse of that reality. What makes this moment so unsettling is not just what Webb has detected, but how easily it detected it. The James Webb Space Telescope was never designed to announce life with certainty. Its purpose was subtler, to analyze atmospheres, temperatures, chemistry, to whisper possibilities, not shout conclusions. And yet, with K218b, the data crossed a line scientists rarely approach. The signal was not buried at the edge of noise. It was clean, repeated, consistent across multiple observations. In other words, the universe didn't hide this one. That realization alone has forced researchers to confront an uncomfortable possibility. If a biosignature this strong can be detected from 120 light-years away, then how many similar worlds have we already overlooked? How many times did earlier telescopes glance at distant planets, see thick atmospheres or hydrogen-rich skies, and quietly discard them as lifeless, when in reality, they may have been alive all along? For decades, Astronomers filtered the universe through a narrow definition of habitability. Earth-sized, Earth-massed, Earth-like. Anything outside that template was labeled exotic, extreme, or unviable. K2-18b exists as a direct challenge to that mindset. It doesn't just stretch the definition of life-friendly worlds, it breaks it. And now, scientists are racing to catch up. Follow-up observations are already underway. Webb is being tasked with longer, deeper atmospheric scans, searching for additional biosignatures. Ethyl mercaptan, methyl chloride, sulfur dioxide, compounds that on Earth are either directly or indirectly linked to biological processes. Each new detection would add weight to an already staggering conclusion. But the most profound question no longer centers on whether life exists on K2-18b. The question is what kind. Life on Earth emerged in a world defined by instability. Violent asteroid impacts, rapid climate swings, massive volcanic eruptions, entire biospheres wiped out and rebuilt over and over again. Evolution here was shaped by catastrophe. Survival favored adaptability, competition, and resilience under pressure. K2-18b tells a different story. If its atmosphere has remained stable for billions of years, if its oceans have persisted without freezing or boiling, then life there would not be forged in chaos, but in consistency. Evolution would not be driven by extinction events, but by gradual refinement. Complexity could accumulate uninterrupted for timescales Earth has never experienced. That changes everything. On Earth, complex life took nearly 4 billion years to emerge. On a world with greater stability and a longer-lived star, that process could continue far beyond what we consider advanced. Not necessarily intelligent in a human sense, but deeply optimized, deeply interconnected, and potentially far more efficient at reshaping its planet than anything we know. And that brings us to the most unsettling implication of all. A biosphere that old would not be subtle. Over billions of years, life alters its environment. It modifies oceans, adjusts atmospheres, creates feedback loops that stabilize climate and chemistry. On Earth, this process transformed a toxic, oxygen-free world into one capable of supporting animals, forests, and civilizations. K2-18b may be the result of that process taken much further. The atmospheric imbalance detected by Webb suggests active regulation, processes constantly correcting chemical drift. This implies not just the presence of life, but a biosphere operating at planetary scale, a system so integrated with its environment that the line between biology and geology begins to blur. In other words, K2-18b may not just host life. It may be a living system, entirely alien in form, entirely invisible to telescopes, yet powerful enough to announce itself across interstellar space. And humanity noticed. This discovery arrives at a critical moment in our technological timeline. For the first time, we possess instruments capable not just of detecting exoplanets, but of analyzing them in detail. Webb is only the beginning. Future observatories, LUVOIR, HabEx, and next-generation interferometers will be able to resolve atmospheric layers, cloud structures, and even seasonal variations on distant worlds. K2-18b is now at the top of every priority list, not because it is close, not because it is Earth-like, but because it appears alive in a way we never expected. Yet for all its promise, K2-18b also serves as a reminder of how small and isolated we remain. At 120 light-years away, even our fastest probes would take tens of thousands of years to reach it. Any signal we send today would arrive centuries from now, and any response would take just as long to return. This is not first contact. This is first awareness. Humanity is staring across a vast cosmic gulf at something that may have been alive long before our species existed, and will likely continue long after we are gone. A planet quietly orbiting its star, oceans breathing beneath a hydrogen sky, entirely indifferent to whether anyone is watching. And yet, the act of observation itself changes us. For centuries, We wondered whether life was rare or common, whether Earth was a miracle or merely an example. K218b pushes us uncomfortably close to an answer. Not a definitive one, but close enough to feel its gravity. If life can thrive on worlds so different from our own, then the universe is not fine-tuned for us. We are fine-tuned for a universe already filled with life. The silence we've experienced may not be emptiness. It may be distance, scale, a mismatch between how life elsewhere exists and how we expect it to communicate. K218b does not broadcast radio waves. It does not flash signals into space. It simply lives, and in doing so, it leaves fingerprints in its atmosphere. Fingerprints Webb was finally sensitive enough to see. This marks a turning point in our story. Not the moment we confirmed alien intelligence, but the moment we realized biology itself may be woven deeply into the fabric of the cosmos. That planets do not merely orbit stars, cool, and fade, but can awaken, evolve, and transform into complex systems given enough time and stability. K218b may be the first such world we've clearly identified. It will not be the last. Every future observation now carries a new weight. Every hydrogen-rich atmosphere, every warm super-Earth, every red dwarf system once dismissed as hostile is now suspect. The galaxy has suddenly become far more alive than we ever imagined. And somewhere, beneath an alien sky, an ocean continues to churn, unaware that, for the first time, a distant species has noticed its existence. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.